this presentation, we're going to talk a little bit about energy transfer in chemical and physical reactions and changes. Now, I haven't introduced you yet, but I am going to now, to the sign delta. Looks like a triangle. And it is a Greek symbol of delta, which means change. So if you see the delta sign, it means change. I'm using it as a shorthand. Another shorthand I'm using in this presentation is RXN, or reaction. So as you see those things, remember that they mean change or reaction. So let's talk a little bit about some of the evidences of a chemical reaction. We've already looked at that, but just a good review. Things like color change, light is emitted or released, fire, sparks released. Maybe we see bubbling. Maybe there's a potential explosion along with some sound. Always a new substance is formed in a chemical reaction or a chemical change. And sometimes there can be a new taste, smell. And heat can be released or absorbed in a chemical reaction. Now we're going to talk a little bit more about heat as it pertains to energy. And energy can flow into or out of a reaction and back out into the system or its surroundings, or from the system, its surroundings, into the reaction. And we classify that through a change of temperature. And we're going to look a little bit more into that in a moment. So some forms of energy, and some of these we've gone over, and some we're going to make sure that we talk about from now until the end of the year. That would be light and solar energy, mechanical energy, or the energy of motion. Whenever something's moving, we say it has mechanical energy. Chemical energy is what we've been talking about in this unit, these modules, basically the energy that comes from breaking bonds and atoms and rearranging it, or the energy required to make new molecules and new combinations, new substances. So that's our chemical energy there. Heat energy, right, the energy associated with heat loss or heat gain. And then kinetic energy and potential energy is basically the energy that's stored up or energy being used. Anytime we see energy being used, that's kinetic energy. And potential energy is energy waiting to be used. Now in this box, part of your chart, the law of conservation of energy, I'm going to go over to the next slide and talk a little bit about what that is. So energy cannot be created or destroyed, just change forms. There's no way in this universe, in the laws of physics, that energy can be created. It also cannot be destroyed. It has to come from another energy source. So the energy is changing forms or transforming. For example, mechanical energy, when somebody's moving, right? Then as they move, maybe they're running, maybe they're at football practice, okay, maybe at a dance class. As they're moving, they're going to produce heat energy. It doesn't just come out of nowhere, but it's energy from that motion that transforms into heat energy and is sent into the system. So energy cannot be created or destroyed, just change forms. Also, matter cannot be created or destroyed, just change forms. So all of our atoms and our molecules, we can't just destroy them. They're going to turn into something else. They're going to transform. Okay, even when we have explosions and things burn, we might be left with the ash. A lot is going to change and become a gas, but it's not just going to disappear out of nowhere. Now let's focus a little bit on physical changes and the heat and energy that happens in those physical changes. In a physical change, we are adding or removing heat, adding or removing energy to make molecules move faster or slower. So by adding heat, energy, from a solid to change to a liquid and a liquid to change to a gas, that heat energy is going to cause those molecules to start to move faster and spread out within their container or the environment, the system that they're in. And removing energy which we would see in a temperature change, right? Then gas gets closer together, it starts moving so much to become a liquid, and liquid condenses even more to become a solid. Make sure you make note of that and include these pictures, drawing your own or finding some and placing them into your video guide. Now let's talk a little bit about chemical reactions and chemical changes, meaning the same thing. In these 4 boxes, I'm going to kind of zoom in, and you can see in your video guide where you need to write certain things. So here under chemical reactions, we're going to talk about these to speed up a chemical reaction. To speed up a chemical reaction, you can add heat, use a catalyst, which lowers the activation energy for a reaction to start. You can increase the surface area or turn the solid into a powder. So if a solid is grinded up into a powder, there's going to be lots more little spots and spaces for the reactants to get together and form a new substance or a product. Also taking a clump and making it like a flat sheet versus a clump where there's a bunch of things kind of in the middle. If there's more surface area, they'll be able to react. Also adding more substance to increase the concentration. So if you have X amount, so many milliliters or grams of a substance, and if you increase that, then there's more of it there to react with the other reactant. And oftentimes even just stirring and mixing, you know that from cooking, that helps get things dissolved or get things to react quicker. Now in our next box of that chart in your notes, you're going to write these 4 points. In chemical reactions, energy is required to form a new substance. It doesn't happen spontaneous. There has to be an initial activation energy. Some reactions release energy during and after a reaction, while other reactions absorb energy during and after a reaction. So we're going to look at what does it look like to release energy and what does it look like to absorb energy in those last 2 boxes in your chart. Now this energy, regardless of it's then released or absorbed, it must be used to break the existing chemical bonds and create new ones. So we've got all these molecules or we've got atoms and they're interacting together, and it's energy to kind of break those molecules and then allow them to rearrange and switch positions to create a new molecule or compound. Now as you can see, for the energy released, we've got a graph, and I want you to make this graph in your notes as well. So in this graph, we have a certain amount of time that the reaction is going to go. And then there's a certain level amount of energy. Down here would be low energy, here's high amount of energy. And this could be any forms of energy. It could be light energy, it could be chemical energy, it could be heat energy. Okay, so we're just kind of lumping them all together. So as you can see, the amount of energy for this reaction to start is about halfway on the graph, because there's activation energy. There has to be enough energy for it to even start, right? Someone's got to start mixing the solution together, or there has to be some heat involved, or other different things for this to happen. So once that initial activation energy is there for the chemical change or chemical reaction to occur, then you can see all this energy is released. And they're releasing energy, and the products are then at a lower energy level than the reactants. The reactants had a higher amount of energy than the products. And as you can see here, reactants have more energy than the products. Energy is usually released in the form of heat and light. To be able to tell if there's been an increase in energy, if heat and light, especially light, fire, sparks aren't released, is to notice an increase in temperature. There will always be an increase in temperature because all this energy is being released. The reactants here are those 2 substances that combine, And the products are those new substances formed that we know indicates a chemical change. Now let's take a look at what happens when energy is absorbed or gained. And I'm sorry this is a little short. Try and extend it out in your notes. Again, just like in the previous example, there has to be an amount of activation energy. It always happens. Something has to be placed into that reaction for it to happen. And then after those reactants start to combine and recombine and react together, there's going to be a lot of energy which is absorbed into the products. And as you can see, the products have more energy than the reactants. They've had to absorb a lot of energy. It takes a lot of energy to make these reactants combine and recombine to form new products. So in summary, reactants have less energy than the products. Energy is required for the reaction to start and go to completion. And there will be a decrease in temperature. So you'll see within the system that the temperature decreases as these products are being formed. A great example of energy absorbing reactions, because we're so used to the ones that release, right? Our big explosions, fire, sparks, things like that. But two energy absorbing reactions would be photosynthesis. It requires sunlight or solar energy for the plants to be able to make sugar and make their own food. And also baking soda and vinegar, your typical volcano reaction. When you combine baking soda and vinegar, the temperature actually goes down. And you're welcome to test that at home if you're interested. Okay, thanks guys. Have a good rest of the time in the module.